Okay, here we go. Thanks everybody for joining. We're starting again the second session of reading through the table read of the monograph on semi-empirical theory of learning, where we're looking at section 6.2 on basically basics of statistical mechanics. And what I wanted to do here is just kind of review a couple of the things that were a little unclear from last time, and then we'll jump into the calculation of the generalization and test errors. So earlier we had talked about there's a section of the paper called Size-Extensivity, Size-Intensivity, and Size-Consistency. This is something I probably added in the last month. So I kind of go through that again. The idea is a key requirement for the thermodynamic limit in statistical mechanics is size extensivity. That physically meaningful quantities, like total energies and free energies, scale linearly with the system size, little n equals capital N. So, along with this, the thermodynamic average quantity should be size intensive, meaning that they remain independent of n equals n, where n again is the system size. As system size increases. So in our setting, size extensivity and size intensivity underpin the large n limit, ensuring that macroscopic observables become independent of microscopic fluctuations. So for those of you who do like statistical learning theory, this is kind of a different way to describe a limit. Um, and it's a little so I kind of want to go through this again. So an example of size example being size extensive. I'll say it like that. We write the data average of the total data sample error. So recall last time we had this data sample error, which is basically the error that the models will make on any given model. You know, this is psi of mu is some Gaussian random variable, and we look at the error that we think we're going to get based on the weights, and we sum that up for all psi mu examples, and when we integrate over psi of mu, where this notation product mu equals 1 to n d psi mu p of psi to the n, this represents a multivariate Gaussian distribution. And so in the large n limit, what we do is we take the limit as little n gets large of 1 over n times this integral. So this is the average of the total data sample error for this, really the model data sample error, where this model data, and where the notation n being greater than 1 means that n is growing arbitrarily large, but it's not necessarily at the limit point at n equals infinity. This is something to keep in mind. Sometimes I found this confuses people that that when we talk about the limit, we're not talking about being exactly at the limit. We're talking about the limit as n grows large. So I could have changed the notation a little bit, which is more of a physics style notation. So the total data sample or total model sample error is size extensive. Whereas the average of this, 1 over n times this average, where again the brackets denote this integral, this is physics notation for an integral, is size intensive. This average is described below and will be very useful in sections 4, 6, and 5. Moreover, this limit will be implicit later when taking a saddle point approximation. So we'll talk about the saddle point below. The data averaged error, so this thing called the data averaged error, this is going to appear frequently below. So this is like a really, this will actually appear all the time. So we talked about it a little earlier. For compatibility with this old paper 8, which is sort of a key paper, we denote using the symbol little epsilon. So epsilon of W is 1 over n times this. We can write it like this, and this is this is size intensive. Now actually this is a little tricky. I have to, technically this is going to be true in the high temperature. I believe this is only true in the high temperature case that you have this nice result, because typically this would be a statistical. Technically, when you compute this effective potential, epsilon of W, we're going to do it in the high temperature case. So I have to kind of check the paper to make sure that I think that this particular result is only useful in the high temperature case. What we call this annealed error potential. But it's what we're going to be using all the time. So I just forgive me, I'm doing a side note. I just double check that how we compute this, and this is all described below. It's just when you're putting something in this section 4.2 has been the hardest one to write of the whole paper. But this epsilon, what we call epsilon W, is the annealed error potential, and this will be made clear below what it is. So it's convenient to write the total annealed error potential as an energy. So we write capital E as in little sub e. So the point of this discussion is just this object is size intensive because it doesn't depend on n. It's divided by n. And this thing is size extensive. And so this will only be useful when the thermodynamic limit actually exists, and this can be reasonably expected for the annealed approximation, which is a regime in which SETOL will be developed. So in other words, there'll be other cases where, when things become non-size extensive, then things get even more interesting. But we're not going to cover those cases. So there's a related notion of size consistency. And this is often introduced in quantum chemistry through the linked cluster theorem. So this states that the total energy or free energy of, in particular, a correlated system scales with m, where m is the number of connected components. Of interacting components. So in other words, you recall that log z is like -1 of the free energy, and this goes mu equals sum over m of the connected components. And here, this is going to look like a sum over cumulants plus some higher order terms. And we're not going to derive the linked cluster theorem. It's a fairly, but this is technically the result we're getting at the end is going to be like a linked cluster theorem. And so this size consistency is going to come up. And then there are a couple of footnotes, as we're working in a physics level of rigor, so we take some liberties in evaluating these origin limits. For those of you who do pure math, that might be quite frustrating or painful, but we're going to leave the formal proofs for future work. And we should note that while our model training and generalization errors are always expressed as energies, an energy is not necessarily a model error. So that's something also to keep track of. So here below, these connected components, these things, will be the matrix generalized cumulants from random matrix theory. And for our neural network, size consistency appears when scaling the number of features. So when this m equals m, number of features in our matrix model, and ensures that our layer and model qualities remain size consistent. As we increase m, just as we do for n. So this is a little different, by the way, than in other statistical mechanics where you might say, I want to increase n, but I want to keep n divided by m constant. And that's it. So that's where so that's a little different than a lot of other formulations. I should comment on it, but that's sort of why we're pointing this out. If you go back and read the old literature, this might not congeal well with what you're seeing. So you should understand this. So for a simple example, in Appendix A2, where we derive the expression for the matrix generalized annealed Hamiltonian. So in this case, we'll see that the matrix generalized annealed Hamiltonian will be size consistent, and more importantly, both size extensivity in n and size consistency in m are crucial here. They justify taking the large n approximation for the matrix integrals and ensures our resulting HCIZ integral, a sum of integrated random matrix cumulants, scales with the dimension of the effective correlation space. So this is sort of a primer for things you're going to see later. And then again, we have this other idea that we talk about once we understand sort of this notion of size extensivity, intensivity, and size consistency. So this is stuff you probably would not see even in a statistical mechanics book, especially the size consistency stuff. That's very it's very important, but it's not something you're going to see in a normal stat mech course. It's something you might see in a quantum chemistry course, but it's something that's really important when you consider what our solutions are going to look like. And then once again, I'll comment that, we define this thing called the average generalization accuracy or quality. And so we introduce this thing, eta, which is a self-overlap in W is 1 minus epsilon of W. So this, we call in the self-overlap, but because it describes the overlap between the true and the predicted labels. And unlike epsilon of W, however, in later sections, we'll first define the data-dependent self-overlap. So we may also define n as the average over the data. And there should be a little in there. I think I caught that. Okay. Thanks for your patience. So this is important. So that, the self-overlap is really the object we care about. And then last time we talked about the various notations, so I won't go into that. I'm going to now jump down to another part, which was a little confusing. So I'll just stop there and ask if anybody has any questions. And I think we're good if nobody has any questions. I can't actually see your faces, so I'm going to assume everything is good. If you have a question, you can also put it in the channel. Alrighty. So now I'm going to go to the last time we talked a little bit about the annealed approximation. So this idea of the annealed approximation and the high temperature approximation, and this was a little confusing. I realized last time we discussed this, so I'm gonna kind of just highlight this again. Again, the idea of the annealed approximation is that you apply Jensen's inequality as an equality. So it lets us interchange integrals and logarithms when computing the data average. So if we have the logarithm over this multivariate distribution of the data of something, we can switch this integral over the data with the log. And sometimes I'll write that as saying I have these two averages. I have the data, I have a thermal average and a data average, and I switch, and what we do is we do the data average first and we do the thermal average second. And so that's sort of the notation that we're using to describe what the annealed approximation is. So in particular, we define something called an annealed Hamiltonian. And the annealed Hamiltonian, again, we talked a little bit about this last time. The annealed Hamiltonian is just minus 1 over n log of this object, which almost looks like a free energy, but it's an integral over the data times e to the minus beta capital epsilon. So again, this is like a data average. It's like the log of a data average, but it is it almost looks like a thermal average of kinds, like a Boltzmann weighted average. It's a Boltzmann weighted average over the data. And what's going to happen is, so when we talk about the annealed approximation, so what I do in the paper is I just show, well, let's use HAM. We can define the annealed partition function. So ZAN is the annealed partition function, which is, again, the integral now mu over the weights times e to the minus n beta HAN, which is this annealed partition function, the annealed Hamiltonian. So if we substitute in this definition of the Hamiltonian into, which is equation 40, we substitute that into 41, and we simplify, and that should be, we just plug it in, and you're going to find that you get back an object which looks like an average over the weights times an average over the data times this e to the minus beta total error. And then in bracket notation, this is just, again, the average over the data first and the weight second. So recall, again, in the annealed approximation, the thermal average, which is the average over the weights, and then the data becomes the average over the data and then the weights. And I didn't realize in 39 I'm using S to represent the weights, and that really should be a W. So this should be a little W here, just to be consistent with the notation. So this is just showing, given this definition of the annealed Hamiltonian, when we plug it into the definition of the annealed partition function, spelling error there. When we plug HAN into this and we work it out, we get this expression again for the annealed partition function. And this looks like, again, where we've switched, it looks like the normal partition function, except we've switched the order of the averages. Then we have this idea of the high temperature approximation. So in addition to the AA, annealed approximation, we'll be evaluating our models at a high temperature. We can form a high temperature approximation if we expand ZAN in a Taylor series around beta. Okay, just sorry, that phrase is a little awkward to me. So in doing so, we'll find that in the AA, the training and the generalization errors are equivalent, and we'll see that below. Consider that's sort of in doing so, that's a comment kind of out of place. But you are gonna see below that the training and generalization errors are equivalent, but that maybe that comment doesn't belong here on 220. So we move on. So we go back to the annealed partition function. To obtain the high T result, we write a Taylor expansion for e to the minus n beta epsilon, where now we're making the independence explicit. We keep the first two terms. We plug this in, and we find out that the annealed the annealed partition function at high temperature actually takes the form of just a average over this annealed potential. So it simplifies tremendously, and this is why at high temperature in the annealed approximation, you get this very nice result where the annealed potential just appears as an average over the weights. So this simple expression shows that the high T approximation suppresses complex interactions between the weights and results in a simple average or naive average. Now, if we have If we have a simple expression
Excuse
for
me.
epsilon, go ahead. You had a question?
Hi, Charles.
Yeah.
Yeah, I have a question. What is the meaning of the high temperature in the case of neural networks? I mean, what is the um, explanation for?
Oh, so typically in neural networks, there's a mapping we try to give here. Where's the mapping? Thought I had a mapping here somewhere. Yeah, the temperature is the amount of stochasticity. So typically, the temperature is something like the learning rate. As you
Oh, right.
or maybe like the amount of noise in the SGD process.
Okay.
So
I see.
that's the idea.
Yeah.
Um,
Okay. Okay.
so anyway, so I just when in the paper I tried to break up the idea between the annealed Hamiltonian, and this really should be. I think this 45 should be Z. I think this should be. I think we're evaluating here on line 1223. I think that's actually uh, this object which we're evaluating. So that really should be ZANHT um, on 1223. So I dropped this little subscript. So this object ZAN, this should be ZANHT. I'm missing an A in there. But that's sort of the steps. And now we see at high temperature, the annealed Hamiltonian is just equal to this. Is just equal to this simple potential. And this is sort of a key idea that in the annealed, the high temperature annealed Hamiltonian, HANHT takes the form of just this annealed potential epsilon of W, and that will be a key result that we use quite frequently. So, and then I sort of go through, and then I derive, and then what happens is if we stick in, if we can expand out, we'll just kind of read through it for you. Let us now express HAN directly in terms of epsilon of W, equation 28. As a thermal average at high T. To do so, let us take a high T expansion of equation 40 by expanding. So 1230. I'll remove that section. By expanding the exponential to first order, again, similar to what we did above. And so we take 1 minus beta times the total error. This gives us 1 over n times natural log. Now we just switch to bracket notation. So this is the same. The second line is the same as the first line. It's just now instead of moving the integral, we're using bracket notation. We then note that because this is an average, that doesn't seem right. Natural log of a plus b is natural log of a plus. Something seems wrong here. I feel like I've done something wrong here. Is that right? Natural log of a plus b is natural. So you take this one, you get this 1 minus, and I was just thinking that we separate that out, and then you should be able to reduce this result. You should be able to reduce equation 46 to 47. I'm just kind of having a brain freeze here to make sure that this is right. Give me a second. Natural log, because exponential of a natural log of a plus b. I'm gonna stop. My brain's kind of freezing, so I'm gonna stop there. And oh yeah. Okay. Here's the part that we use the result that the property that natural log of 1 plus y is approximately equal to y. So this step is wrong. So that line is wrong, and I'd forgotten. That's why I'm having my brain stop. We're actually using this property. So this third line here on equation 46, the third line doesn't belong there. I'm sorry about that. So in order to show that the high temperature approximation, we actually use this approximation, that natural log, and so we go from the second line to the fourth line. So this somehow, I don't know how that got in there, for y much smaller than 1. So in other words, when the error is small. So when the error is small, we can make this approximation, and that's actually a comment that is important also. So in the high temperature approximation, beta is small, and so since beta is small, this term becomes small. So this term is y. The beta times capital delta is y. That term is small because we're in the high temperature approximation, and therefore the Hamiltonian can be reduced to this simple form, which is just the annealed potential. Moving forward, we'll assume that we are taking the high temperature limit like this. So this is what we're going to be doing. And again here, given 47, we can now express the annealed partition function of high T directly in terms of the annealed or data averaged error. So again, ZANHT is the integral over the weights times e to the minus beta in H, which then becomes, and notice that H is size intensive. H is size intensive because it's an intensive quantity because it's divided by n. And so we get minus n beta epsilon. And this is a key result that we're going to have. So now we've reduced the potential to look like a thermal average over the weights of just this annealed potential. So equation 48 is really a critical thing we're going to use all over. So if we assume that at high T, we can make this approximation, since we only care about the small beta results, this will prove very useful in working with HCIZ integrals. Okay, so that's kind of where we stopped last time, and I kind of get through that. And if there are any questions, let me know. Otherwise, I'm going to move on to this next section. Okie dokie. So the next part is really, now we're getting into the meat and potatoes of statistical mechanics, of how we do neural networks. So far, everything has just been just vanilla statistical mechanics. So what we're going to do is we're going to define in statistical mechanics how we compute the average generalization error and training errors and their generating functions. And I need to sort of add something to the beginning of this paragraph, is that when we define this is the training error and this is the generalization error, and we call them energies, but average energies, but they're errors. You'll notice that we use the partition function Zn to directly compute the annealed training and generalization errors. And the point is that the training error is how the free energy changes with respect to changes in temperature. So in other words, how in statistical mechanics, the training error is how much the free energy, this natural log Z, which is essentially the free energy, the average free energy, how much does the average free energy change when you change the amount of noise in the training process? And that's what we mean by the training error. So it's not, in statistical mechanics, the training and the generalization errors are not necessarily defined by the specific distributions. That is, we don't have a training set and a test set and you separate them out and you do this. It's a little different. This is all described, and again, I'm sorry it's not in the paper, that's why we're doing this. This is all described in a work by Sola, and she has some work from like the early 90s, and then she has some recent work from a couple years ago where she goes into great detail about how to derive these expressions and their relationship to Bayesian inference. But it's a really important idea to realize that in general, in statistical mechanics, the training error really was related to how the free energy changes with respect to the amount of noise in the system during training. And the generalization error, or the test error, is how the free energy changes with respect to adding or removing a piece of training data. So it's not really defined. So I think in machine learning, you have this sort of bias variance theory, and you define things in terms of test sets and training sets. And we're not doing that. And I think it may be equivalent in some sense, but you have to go back to Sola and understand detail what she's doing. But this is sort of the key idea. And what's going to happen at high temperature is these two things are going to be the same. And I don't know. I always wonder whether I should put that at the beginning or not, like right after 49 and 50, that these two are going to be equivalent at high temperature. And I probably should say that, then we prove it. So if you write, the average training error is defined as the data average of the thermal average of the model error. And so it's 1 over n times this thermal average. So here's the model error, and here's the total model error, really the average model error, of the thermal average and then the data average. And again, by applying the annealed approximation, we can switch over the integrals, giving the thermal average over the weights, the data average model error. I don't know why the LaTeX is screwed up. But then, so you have 1 over, so you see we've switched the order of these two integrals. And in the case of the high T, you want to obtain the expression in terms of the annealed error potential, which we talked about earlier. So you get this nice result where the high temperature annealed training error is just the thermal average of this epsilon of W. And you may recall that appeared here. This is what that object looks like. Well, excuse me. This is the partition function. This is the normalization for this object. So this is an average. The training error, we can obtain the training error by taking the partial derivative. What is this? Of f. Like so, this expression is, so 54 is the same as 49. So 54 is the same as 49. For some reason, it's, yeah, I don't know why 54 and same as 49. This stuff kind of got moved around a little because Mike was complaining it's too long and confusing. So I like to have all the derivations. So this is basically the same object. So we can write it again like this. I need to go back and check why 54 is basically the same as 49 or Zenus. And so we get this, but you get basically this expression. I think what we're doing, I see. We're basically just deriving this. We're proving 53. So if you go through and kind of work out all the math, what I tried to do in this section is just derive everything pedagogically very carefully. But it may have gotten a little mangled in terms of the explanations. So these are definitely the definitions, and sort of we're writing it using the annealed approximation, and then what we do is we prove it. So the language here may be, I don't like writing theorem proof, but basically derived it. So this little section derives equation 56, which is this key result. Here, the model data variables don't enter the calc. Now, notice that the model data variables do not enter the calculation because we integrated them out before the calculation of the thermal average. This is actually a key thing because not only when you integrate out the model variables, and I should comment on this in 1258, you also integrate out the dimension of the vectors. So it turns out that the M dimensional doesn't appear. And our sign convention is consistent with the model of neural network training that minimizes the total loss or ST error and therefore minimizes free energies as well. So now we go to the average generalization error. So now we'll compute the average generalization error in deriving. And so again, all of this is just basically the same thing over and over. We're just deriving, these equations. Again, 58 is actually, 58 is, I think, the same probably as, where was it? I think 58 is 50. So again, this might be a little messy. I have to go back and reread this very carefully. 58 is 50. But again, we average generalization error. In deriving the average generalization error, we apply the high temperature approximation to the Hamiltonian to denote HA&T, but then we'll consider the full thermal average of the annealed potential using HA&T as the definition. So we have EHA&T general is this average. This should be that in 57. That should be that S should be a W. But the idea is now, what does it mean to take this average? We take the integral of d mu of W times epsilon of W times our annealed error potential. And then this is, because we're at high temperature, this is d mu of W epsilon of W e to the minus beta E of W. So this is what it means to take the average. That's the definition of the average. But we're not going to do that. So we will not, however, compute this thermal average directly, but instead we use the generating function. So again, this is the idea. The average generalization error is given by the change in unitless free energy with respect to the change in number of data points. So this is the reference to SOLA. So again, this section got a little mangled. So again, this is equation 58, but you notice there's this extra term, and we're just going to ignore this term because it's constant, and you can go to SOLA and you can see where it comes from. So again, where ZB is a constant normalization term depends on lambda beta. To obtain the average model generalization accuracies or the layer quality, so 1272. So these two sentences need to be flipped. So we see now that in the average, in the annealed approximation at high temperature, the average training error is exactly the average generalization error. So this is like a key result. And there should be a little beta on 59. That's a thermal average. Should be a little beta there. But this is the key result we're trying to prove for this section. So maybe like this, maybe 59 should be, where were we? Like 59 should be right here. We're going to prove these two objects are the same, and that's what we do in this section. And then we say to obtain the model average generalization accuracies or layer quality, we define new generating functions. So this line can basically be cut because we're going to say it here. So we've defined now, we've shown that at high temperature, our definition of the training error and the generalization error are the same. And they're basically the thermal average. Again, there should be a beta here. They're a thermal average of this annealed potential, which is basically the Hamiltonian. To define the, and I'm going to stop here. Does anybody have any questions? Because I kind of skipped around a bit when talking about this.
I have a question. So you said that at a high temperature, the training error and the generalization error are the same.
Yes.
So that probably can be understandable from the neural network's point of view. What normally what we have in neural networks is they are different, right? Because the training errors the error is lower than the generalization error in general.
Right.
So we are in the high temperature where there are a lot of stochasticity. Then what you are showing is that these errors are the same.
Yes, and remember that although we have to go back and look at SOLA, we're really looking at something a little different, right? We're saying that we're not defining the errors distributionally. So we don't say there's a training set and a test set. What we say is that when you have high temperature, adding a new example to the model is the same as adding a lot of noise to the model. So when the model's very noisy, when you're in the theoretically, this is all theoretical stuff, right? I mean, it's just a way of form. It's all formal. It's just saying when you have a lot of stochasticity, it's very easy to add a new training example, right? Because adding a new training example almost looks like noise. Now, how the new training example, it looks like a noisy version. The new example in evaluating the model on a test set is almost like looking at a noisy version of the training data. Right. So, right, yeah. That's the idea. If I add noise to the training data, that's almost like turning it into a test data set.
Right.
That's what it's saying.
Yeah, when there is a lot of stochasticity. Yeah.
Right. So a noisy training, and that's I'm going to add that. A noisy training example looks like a test example. That's the idea, right? So there's no difference. So in the theory, a noisy training example would look like a test example. And so the theory is treating both cases. And again, this is more of a formal thing, but that's a great question. Okay, now we're going to talk about something called the model quality. And this is just 1 minus the error, right? So we're talking about accuracies. We want to talk about accuracies instead of energies, instead of errors. We want to talk about accuracies because we're going to be deriving a form for the accuracy. So we're just going to define the quality as 1 minus. So for the student-teacher model, it's 1 minus the error on the student-teacher. And we talked about the student-teacher model earlier in the paper, so it's a little out of context here. But for our purposes, we would define the model quality as an equation 7, which is way back in the paper, as our approximation to the average generalization accuracy for our model. We denote the model quality for the student-teacher perceptron model as bar QST, and for a general network as bar QST. Oh, that should be an NN. 1279 should be an NN. Such that QST is 1 minus E ST generalization, and QNN is 1 minus the epsilon neural network generalization. So this is our definition. And of course, we're at high temperature, so it could also just be 1 minus the training error, right? They're going to be the same objects, right? And we might even want to note that in 60 and 61 that they're basically they're going to be the same, because we're going to be at high temperature at all cases. We also define a layer quality, simply denoted a general layer quality, denoted as Q bar, which will describe the contributions of an individual layer makes to the overall quality. That should be This is going to be a little confusing, but it won't matter until later. To obtain the layer quality, we defined an accuracy or quality generating function denoted gamma q, which is analogous to a free energy, but with the opposite sign convention. So, for example, the single layer student perceptron, the average q is going to be n minus f. Where n is the number of free parameters in the model and is in units of energy. So why is it not 1? So here we have to be very careful on 1, 2, 8, 4. Here, when we define these generating functions as 1 minus f, you have to be very careful whether you're looking at the average free energy or the total free energy. The total free energy, recall the total free energy is size extensive, so it would scale as n. And the average free energy is size intensive, so there would be a 1 here. So that's why this should be the average. So this is why it's a little confusing. This part of the paper is really hard to describe. 1 minus the average f. So I have to make so this is why, like, keeping track of whether this is n or whether this is 1 is really tricky. I mean, conceptually it's not hard, but like when you write the paper, you have to be really careful. So I kind of want to clean that little part up a bit. But generally speaking, so the quality generating function in the annealed approximation high temperature is identified as beta q is natural log of the average over w of e to the n beta eta. So now we have this object called the self-overlap. And I should put a comment in 62 that, just to point back to the definition. So recall, so this is 1, so this is going to be, why is it 1 plus? It should be 1 minus. So I'm looking at this, and this should be 1. You're going to stick eta in for, you're going to put epsilon in, and it's going to go through, and there should be a minus sign here. I don't know why we're missing the minus sign. There should be a minus sign on the n. So we're missing a minus sign in equation 63, and there's a minus sign missing. But basically, I'm just plugging in for eta is 1 minus epsilon, not 1 plus epsilon. And if you derive it all out, you're going to get beta n minus n ft. So we plug in the equation for eta, which should be 1 minus. We then separate out, so it would be e to the n beta, e to the minus n beta epsilon. And then the natural log of a product is this. The natural log of this product is the sum of the logs. So you get natural log of the first integral, which is d mu of n e to the n beta, plus natural log of the second integral, d mu e to the minus n beta e. And so this gives you natural log n beta plus natural log d mu of w minus n w beta e, and that will be beta n minus the free energy. So we recover this idea that the quality is just n minus the free energy, or 1 minus the free energy, depending on the normalization. And again, this object f of st, there's no st there. Well, it's okay to have, you don't need the st. This isn't a simple case. The why it has st is this is just more generally. So the reason it's st is because it's really because it's for a vector model. And when you go to appendix A2 and A3, you'll see that this is a little different with the matrix models. And again, this object, the free energy, was just defined as, recall the partition function has the minus, right? So it really should be a minus. And recall the free energy is minus log of the partition function. So minus log of this object in 48 is what appears in this equation here. So that should reference equation 48. And that's what's going on. So we're going to define this idea of equality is going to be n minus the free energy, or more generally, the average quality. And this is terrible that 1289 doesn't know. It says the average, the n-dimensional average. So you basically divide everything by n, and you get this result. The matrix case is a little more complicated. And so in the matrix case, we do in equations in appendix A3. So in the appendix, we do this much more rigorously with using the full statistical mechanics. But in the end, you get, likewise, one can show that the quality in the annealed approximation of high temperatures can be identified as the thermal average of the data average or annealed self-overlap. So the quality object is just the average. Again, that should be a W. I'm sorry, sometimes there's a macro in the paper, and I'm using the wrong macro. That should be it. When I write this thermal average, that should be a W, and this, of course, should be in 64. There should be an N here because it's an average over all in data points, and then and so you end up with this average over the self-overlap. So the average quality is the average of this self-overlap. It's the thermal average of the self-overlap. This is a core, like equation 64 is a core result, which we're going to use later. This will be the object which gets generalized for the matrix case. We can obtain Q by taking the appropriate partial derivative. Again, as above, we're not actually going to evaluate this average. In other words, we're not going to do, we're not going to write down this, where this now is instead of epsilon, we have an eta. We're not going to write it down in this form. What we're going to do is, again, use the generating function. So this is in statistical mechanics. The idea is when you're going to compute an average, you don't actually compute the average, you use the generating function. So for technical reasons, we'll actually define and use the generating function for the average layer quality squared. So we're actually going to compute the layer quality squared, not the layer average, in analogy with equations 50 and whatever that's supposed to be. I don't know what it was. And at high temperature and at large N, we can obtain the layer quality squared, see section 5, 127, as the limit as capital N gets larger, because we're going to be d beta, beta, gamma q. 65. And this actually is equal to, this is not quite right. I don't think 65 is right. I mean, generally, we're gonna take a derivative. This object actually could be. I think there should be a 1 over n here. I can't remember if there's a 1 over n or not, depending on how we define it. It's very, very technical. But basically, this is an analogy with this equation. Actually, should be. Yeah, this is fine. We're taking the derivative of we're taking the derivative with respect to beta. So, and recall that the average training error and the generalization error are the same. So when we get to equation 65, and I'm sorry, there's probably a typo here in 65, the quality can be either the beta derivative of this object times 1 over n, or it can be the n derivative of the object times 1 over beta. So in other words, we're plugging in gamma, we're putting this generating functions going here, and there's no minus sign. And so we can either take this derivative or we can take this derivative, and they're equivalent. And it's just, there's a technical thing with, so I got to check 65. There's probably a typo there, but that's what's going on. So we're going to define the quality in terms, just as if it were a free energy, and take the appropriate derivative. Okay, take a break for a second. Now we're going to talk a little bit, that we get a little more, now things get a little more sophisticated. So to evaluate Q, we're going to take a large N limit, which is in the thermodynamic limit, which we assume going forward. So now we're going to talk, there's technically, the thermodynamic limit and the large N limit are technically a little different. And I'm going to talk a little bit about that. So, as I say it there, note that technically the thermodynamic limit and the large N limit are different. The thermodynamic limit typically refers to the case where all thermodynamic averages remain size intensive as the system size increases. And while this does refer to n equals n growing large, frequently there's an additional constraint, such as for neural networks, that n over m equals n over m remains constant. So this, I talked about this a little earlier. I was wondering where we're going to talk about that. So this is called the load, and typically you might say the load, which is n over m, this would remain constant. We're not doing that. So for the student-teacher model of perceptron, however, the thermodynamic limit averages we need do not depend on m. So recall, we integrated out over the data, and because we integrated out over the data, the m dependence goes away. We integrated it out. So this constraint is not necessary. Moreover, later when we form our matrix generalization of the student-teacher model, we would not enforce that n over m remain constant, but instead the final result will be size consistent in m. So this is a technical thing. If you know anything about statistical mechanics and you read any of these old papers, in particular, you might see this. And even if you read the old papers with Mahoney and I, we talk about this idea of n over m being constant, being different from the VC limit. But in this work, we're doing something a little different. So here, the thermodynamic limit is the large n limit of the model as n equals n grows arbitrarily large, i.e. n is much greater than 1. So to express the average free energy in the large n limit, we can write the average minus beta f n. The average is limit as n gets large, 1 over n times the natural log of basically, this is the partition function, right? So that's what it looks like. With this large n approximation, when this large n approximation is well behaved, then the total energy epsilon is extensive, i.e. when this epsilon, when capital E equals n times little epsilon, and consequently the total free energy is also extensive, F equals n times average F. This is the cornerstone of statistical mechanics as allows for meaningful macroscopic properties from microscopic interactions. So it's a little difficult to explain. Like sometimes we see, remember I said before, sometimes you see the n, sometimes you see the 1, but this is sort of the key idea is that these averages, they don't like, you don't like, if you were non-extensive, then F might include some term which is like depends on n squared or depends on log n or has some funny behavior. And that might be, for example, the evidence of a phase transition, something like this. So then we talk about this idea in statistical mechanics of self-averaging. The existence of the limit signifies that the system is self-averaging, meaning that the macroscopic properties are independent of fluctuations. This also implies that the relevant averages, the triangular generalization errors, are the same for almost all samples or all realizations of the disorder. Additionally, the annealed and quenched averages, natural log, log of the average and average of the log, respectively, become sharply peaked. So basically, the average of log z becomes log of average z as n goes to infinity, although they're not strictly equal except at the limit. So for a neural network, self-averaging implies that the weights are typical of the distribution, and therefore the neural network can generalize to similar but unseen test examples. This is actually a really critical idea, and it's something that took me a long time to realize, like, what's going on. We talk about the weights being typical. So when the weight is typical, you expect things to generalize. When the weight is atypical, if something is weird in the weight and it's atypical, then you can't apply it to something which you haven't seen before because it doesn't behave. So this is the idea of why when this self-averaging breaks down, we think that the layers are overfitting. They overfit the data and they can no longer describe out of sample data. And this is a key idea that we actually use in the paper. This idea that when things become atypical. So, for example, some of you on the channel might know I've talked a little bit about correlation traps, and I'll talk about that later in the paper. A correlation trap is an example of where the weights become atypical. And therefore, they probably, and we show that when the weight matrix becomes atypical, you end up having a weird overfitting effect. Another example of atypicality would be when people are training a model and they clip the weights. So when they clip the weights, it's because the weights are becoming too large, they become atypical. Okay, so another key idea we're going to look at is called the saddle point approximation. So in the saddle point approximation, when the thermodynamic limit exists, we can approximate the free energy and or the partition function in the large n limit using the saddle point approximation to evaluate the asymptotic behavior of the integrals we encounter. In the case of f and or z, we assume that we can apply the saddle point approximation, meaning that, and I really should have here at large, this should be like at large n, this should be, when n is large. So 68 means n is large. We can basically approximate the integral we approximate the integral as its peak value. So this is a really, again, a key idea. So this integral, we just get rid of it, right? There's an integral, it goes away. There's no longer an integral. Now it's just this. It's just we just evaluated at W star, where W star satisfies these saddle point equations, right? So they satisfy that the first derivative is 0 and the second derivative is greater than 0. So in other words, this is some convex point. So this is a very simple idea, right? We have an integral, we just replace it with its peak value. This is a very common thing that people do all the time. The thing is that they don't always check the conditions. So a very typical thing you'll see in statistical mechanics is someone says, well, I'm going to assume I have a saddle point approximation. I assume I have these conditions. They don't really check the, maybe they'll check the conditions, maybe not. And a lot of why statistical mechanics has been ignored in the machine learning community and the mathematicians is because they make these kinds of approximations, but they don't know how to check the conditions strictly. And sometimes the conditions hold, and sometimes they can't, and sometimes you can prove them, and sometimes you can't. But this is the idea, that we have this thermal average can just be replaced by its peak value. And this is a core idea. So to apply the SPA rigorously, we expect that epsilon decays exponentially. This is important. The error decays exponentially, whereas we will be working with, now we're going to be working with heavy-tailed parallel distribution. So it's not totally obvious that things will decay exponentially. At first glance, this might seem problematic. These distributions, however, can also be modeled as truncated power laws because of finite size effects. This suggests we can apply the SPA formally, assuming but not checking that the finite size effects will satisfy the general requirements. So, and the SPA will play a central role when we evaluate matrix generalized form in the HCIZ integrals. So again, here's an example we talked before. I was kind of talking, but I'll just kind of read it. We should note that when the thermodynamic limit fails to exist, the free energy will contain additional non-extensive terms. So F is N plus some term which is not extensive, right? There's some term which depends on N to something. Could be 2, could be 1.5, could be anything. But this is not extensive. In this case, the annealed approximation may fail, the SPA may not apply, and the system may fail to achieve self-averaging. This causes the system to behave atypically and possibly converge to a metastable interglassy phase. Indeed, when the weights are atypical, they may describe the training data well, but they would fail to describe the test data well. In this sense, we say the model is overfit to the training data. We will not explicitly consider a model that is not extensive. However, we will present results where we suspect the model is overfit, section 6.4, and additionally where we observe glassy behavior, which we refer to a hysteresis effect. And so we have a very, very long, Chris, who is one of the co-authors, did a lot of work studying what happens when trying to force the system into this weird glassy behavior and using the theory to try to understand what happens. Okay, so there's a remark here. The remark is additional results are provided in A2. In particular, in Appendix A21, we use the ideas from this section to derive the full nonlinear vector form of the annealed Hamiltonian for the linear perceptron and the annealed approximation. We express it at high temperature. There's no beta there, so 1348. That beta. That red beta goes away. Then in equation A21, we derive the matrix form of the matrix generalization. So HAN of R goes to HAN of R of these quantities. This derivation is necessary to obtain the normalization on the weight matrices necessary for the final results in section 5. Okay, so that's sort of like this section on the thermodynamic limit, these saddle point approximations, self-averaging. This is like really subtle stuff that takes a while to absorb when you start getting into deeper statistical mechanics. The last part, I'll see if I can get through since we have a few more. I'll try to squeeze an extra 5 minutes in here for you. This idea of these HCIZ integrals. This is some fairly advanced random matrix theory stuff that we're going to use. This is sort of the core idea. And so to generalize the linear student-teacher perceptron in the annealed approximation at high temperature to form from perceptron vectors to MLP matrices, we need to generalize the thermal average over m-dimensional perceptron weight vectors to an integral over student n by m weight matrices. The resulting partition function of free energies will be expressed with what is called an HCIZ integral. See, a variety of references on this. Analogous to equation whatever. I don't. What equation is that? I don't know. We will define a layer. The layer quality generating function. Okay, so the layer quality generating function takes the form of an HCIZ integral. So it's going to be defined without the 1 over n. So it's just so this the free energy is the natural log of something. So this is the object we were looking at earlier that I in 65. It's the integral over some matrix, some measure over a matrix, times the exponential of n beta trace ax, and where a2 and x2 are defined earlier in the paper, in like section 3. This is approximately with the n beta trace g of a. This is evaluated in the large n limit, here meaning n gets large, but not at the limit. Here, a and x are n by n Hermitian matrices. D mu is a measure over all random orthogonal matrices. And this object is something called we call it it's some kind of norm generating function, but it's not like gamma. It's something else entirely. Defined in equation 32, section 5. So in applying this, we're going to write. So the rest of this, you have to, in order to understand this part, you have to have read section 3. So I'll skip it. But basically, the idea is that this object, before we talked about this thing called the linked cluster theorem. And we said that we're going to be able to get some object which is natural log z looks like the sum over m components. So you'll recall that we talked about that here, way up here. Where is it? Sorry, give me a second here. Where's the linked cluster theorem? It's way up here, probably. All right, I got lost. I'm sorry about that. Here, linked cluster theorem, equation 30. And I don't link back to that, but I want to make this clear. This idea of the linked cluster theorem is a sum over m cumulants. So when you get down to the HCIZ integral, it turns out, and the linked cluster theorem is very general. It's used all over the place in quantum chemistry, couple cluster theory, certain areas of statistical mechanics. This is a sum. This is a trace G. So this is actually a sum over m effective cumulants, where this thing G is actually an integral over... This thing is an integral over R of z, which is an R transform, which is actually a generalized cumulant. It's called the R transform, but it's actually a generalized cumulant. And we get this sum over m tilde components, where m is actually is part of this reduced rank space. I don't know why this G looks different than this G. Son of a. That's why I'm kind of skipping this. I haven't actually read this yet in a while. But that's the idea, is that you define this free energy object, this 1 minus free energy or n minus free energy, which is a generating function. And at large n, this becomes n beta times I equals 1 to m tilde over the eigenvalues in the effective correlation space, which are the tail of the distribution, integrate over this integral over RZ, which is actually a cumulant function. So you return back to the linked cluster theorem. And I'm just going to note, you notice that this final result depends on n and m. And you recall this is a generating function. So it's like a free energy. And we're going to take derivatives. And when we go back to equation 50, and we see we're going to take this object's going to be stuck into this. We're going to stick that gamma into this equation. We can take the derivative with our beta and divide by n, or we can take the derivative with the n and divide by beta. And you'll see that since this object is just a fixed number, this thing won't depend on n or beta. Both of these will cancel, right? So now you see that when you, in the high temperature approximation, that the training error and the generalization error both become equivalent and are simply the appropriate partial derivatives of this object, which looks like a free energy or as a generating function, and satisfies the linked cluster theorem. Beyond that, there's a little section here on branch cuts. I won't go into that unless somebody wants to ask questions about it, since we're out of time. But later in the paper, this object R of z is a complex function, and because it's a complex function, it may have a branch cut. And it turns out that the branch cut you select is exactly the branch cut corresponding to this restriction of the integral to a low rank space, which we don't discuss here. But this is actually a critical idea, that the branch cut corresponds to this. So when you get into some of the deeper statistical mechanics, this part will be very important. But I'm just going to stop here. So I'm going to stop. we've gotten through most of section 4.2. Once again, I appreciate your patience. It needs a little more editing, but this is sort of your basic introduction to statistical mechanics. So this is sort of, and then in the rest of section 4 and in the appendix, we're going to use these ideas to rederive some old results from the 90s on the generalization error of a perceptron in the student-teacher model. So we're gonna go through and derive all of this from scratch. We'll do it in a simple case using in the annealed approximation and high temperature, and in the appendix we do the full derivation using all the machinery statistical mechanics. So you can sort of see the setup of the problem, and that's just to get us to set the problem up, which then eventually will be then. So we won't even use this stuff yet. We're basically the next few sections are basically to get us to this. How do we derive equation 64? So a lot of, so the next section, the rest of section 4.2 is just how do you derive, the rest of section 4 is how do you derive equation 64 for the simple case of a student teacher, which is just a perceptron model or a vector model of a neural network. I'm going to stop there and open up the floor and ask if anybody has any questions. How do I stop screen share? So I appreciate you guys going through this with me. Are there any questions? I'm going to, how do I stop? Oh, I don't know how to stop sharing. So I'll just let you guys ask questions. I'll stop streaming.
I have another question.
Go ahead.
So, if I understood correctly, the main objective of this semi-empirical theory of deep learning is to have some kind of thermodynamic associate to, let's say, the calculation of the generalization error, some average generalization error, something like that. To
Yes,
have some kind of
that's right.
thermodynamic rule.
That's
Okay.
right.
Okay.
For the layer. So what we're going to do is we're going to compute the accuracy. How much does each layer contribute to the accuracy or really the precision of the model? That's what we're doing. And so each layer will have its own component that it contributes to the model. Right? Because it's a multi-layer perceptron, right? So each layer has, so it's a theory of layer convergence. So we want to understand how do the individual layers converge. That's what we're trying to do.
And then another question: why are you using this student-teacher neural network? It's just for a tool to get a more general multi-layer perceptron later on.
Yeah, so the student-teacher model will allow us to formulate it allows us to formulate the problem in terms of this HCIZ integral. So let me try to do the screen share again. You can't see my screen, right? Hold on, I'll do it again. How do I share the screen? I should have not stopped. Make selection, this window, share this window. So we're trying to get to this HCIZ integral. This HCIZ integral is going to allow this object, when we evaluate this object, it's going to turn out to be, we can prove certain properties of the convergence of the theory by understanding how to evaluate this integral. And the student-teacher model is a general model from statistical mechanics, which lets us evaluate the generalization error or something like the precision of a model. So we have the that's why we're doing this. So we're trying to get to this point where, in fact, we can derive. We have this HCSR theory, which we published in 2020, which I worked on for many years, which shows, which is behind Weight Watcher, which says layers that are more heavy-tailed in power law perform better. And we're actually going to prove that using this approach. So we're going to prove that these heavy-tailed layers actually, that we're going to show why being heavy-tailed works, and why being power law and having an exponent of 2 is very, very important. Like why that's the limit point. So we're going to actually argue that every layer in a neural network approaches an ideal state. And that ideal state will, as actually we talked about it a little earlier in the paper. I can find it in here. The ideal state of the layer will be one where the power law exponent is 2 and it satisfies the renormalization group condition. So it's somewhere in earlier, we talk about it here, and earlier in section 3, where, well, it's hard for me. I don't have a table that explains. I was hoping it'd be a table. But we're going to show that there's this condition called the renormalization group condition from theoretical physics and statistical mechanics, and we're going to show that the layers satisfy this condition. When they satisfy this condition, we're going to see that the power law exponents align to be 2, which is what was predicted by the HCSR theory. So we're actually going to show that the results that we predicted in 2018 and published in 2021 are actually related to something very, very deep in statistical mechanics called the Wilson exact renormalization group. And we're going to show this empirically in the paper, that these two ideas align and can be proved analytically.
All right. Okay.
And the idea is like when you're training a model, that like, and then the theory is like when you're training a model, how do we obtain a model which has the highest quality possible? How do we get every layer of the model to be ideal? And so that what the theory is saying is that when you train your models, you should try to get all the layers to look like this. And nobody does that, right? Right now, people train giant models and they compress them and they distill them. And there's all these things you have to go through. And what we're trying to do is say, we think we have a theory which would tell us what a perfect model would look like. Like, what would a perfect model look like? Here we go. Here are the perfect model. The tail of the ESD can be fit to a power law of exponent alpha equals 2. The eigenvalues of the tail satisfy the trace log condition, natural log equals 0. The generalizing components of the layer concentrate to the singular vectors associated with the tail of the ESD. So this is a theory. We're making a prediction that this is what the ideal state of learning of any neural network would look like. And then we're running experiments to try to show that you can get to that state. That's the whole point of this. Like, that's like the 10,000 foot picture of why we're doing all this.
Okay.
And we could talk about that. I was just sort of, this talk was more about like just introduce people to statistical mechanics, because it's, in order to understand how to do all this, you have to have this machinery. You know, you have to know what a saddle point is. You have to know what an HCIZ integral is, this kind of stuff. But we can talk, you know, we can go and talk early. I can do another session where we talk sort of earlier in the paper, like section 3. That might be a good thing to do.
Yeah. Yeah.
So I can do that next time if you want.
Yeah. Very interesting.
All right. Any other questions? Okay, great. Look, I hope you got something out of it. So my goal here is, section 4 is really just about, this is just statistical mechanics. This is just basic statistical mechanics, right? And so we're just kind of setting up the math so you'll be able to read the rest of the paper. So you have the machinery. But this is just sort of the techniques. This isn't even really why we're doing it. Go ahead. There was another question.
Yeah. Can you hear me?
Yes.
Great. It was going a little bit back. It was there was some terms that was used called realizations of the disorder, and I was thinking that was dealing with the stochasticity of the something dealing with the Gaussian distribution that was introduced into the model.
Yes.
Is that what that is? Okay.
Right. So
because go ahead.
So in statistical mechanics, in the theory of statistical mechanics, you have this idea that, and I'll talk about this, actually, we talk about this in section 4.3. You know, think about how you train a model, right? I train a model and I learn the weights. And after I learn the weights, I evaluate it on some data, right? That's how you evaluate a model, right? If you're getting hired, if you're fine-tuning a model for someone, you go in, they pay you some money, they fine-tune the model, and you run your eval, right? That's what you do, right? That's just operationally what you do. I think somewhere I have a picture of this somewhere. Maybe it was down here. Sorry, give me a second. I'm trying to find it where I'm paging through here. Yeah, right. Okay. In a theory, so in when you do a theory, you know, instead of learning the weights and averaging over the data, we're going to average over the data first. We're going to pretend that we have this fake data that we're going to average over, and then we'll average over the weights. So in other words, normally you would, so this inner integral means, oh, I learn the weights, should be a W, but it's an S. I learn the weights, and then I average over the data. That's operationally what you do, right? You learn the weights, you run backprop, then you average it. What we're gonna do is we're gonna create a Gaussian model for the data, and we're gonna integrate out all the data. So that Gaussian model vanishes from the theory, and then we're gonna end up with theory which is expressed solely in terms of the weights. And that's why we can look, that's why the theory is Weight Watcher, because it's a theory of looking at the weight matrix and trying to understand what it is. So typically in physics, they say you're averaging over the disorder because the training data is kind of like the disorder of the system. And that's what it means. You average, when they say they average over the, when we say we average over the data, in statistical mechanics, you say we average over the disorder. That's what they mean. And when we say we learn the weights, or we run an approximation algorithm in statistical mechanics, you say, well, we're not going to learn the weights. We're going to take a thermal average. And so we take the thermal average, and that tells us, that average tells us about the weights. And in our case, that thermal average is going to be a saddle point approximation. The thermal average is, where is it? Is the HCIZ integral. So instead of learning the weights, we're going to say, oh, I'm going to run this thermal average, which is an HCIZ integral, and I get an expression, and that expression I then feed in the spectral properties of the weight matrix into this. And so instead of learning the weights, I learn the generalization error by looking at the weights. That's what's going on. And I
Yeah,
know
that's impressive. No, that's impressive.
Yeah, it's a bizarre way of doing things. I understand. I'm sorry.
Correct.
Go ahead.
Yeah. So when looking at this, I was seeing that this generalization error, basically from the machine learning perspective, but when we transverse back over, it's really the minimization of free energy is what we have to do, right? Look at minimizing the free energy.
Yeah, I mean, there's a the free energy is like a marginalization over a variable. So in this case, when we talk about the free energy, we're marginalizing, you can marginalize over the data, and then we marginalize over the weights. So you minimize over the weights. We write in terms of free energy, right? But technically they don't evaluate the free energy directly, when they do statistical mechanics, because you would have to know the full partition function, and they don't know it, and they don't know the partition function. So they do what's called partition free. So the idea is you can minimize some energy function, which somehow doesn't require you to evaluate the partition function. We are evaluating the partition function, right? So they're doing something rather nasty.
And I noticed, so when you evaluate the partition, it was over the sum of the entire network, and then getting the layer from that, right? To evaluate the layer from the total of the network where it's at, right?
Right. I have to. So earlier in the paper, way up here, I have to figure out some way to write down the total quality of a model, because it's a complicated object, right? It has, it's somewhere in here, like right at the beginning. Like we have an energy landscape with the energy function, the output. This is the thing we minimize. Then I'm going to write down, go down. And again, we didn't really go through the beginning of the paper, but somewhere in here I write down the equation 7. There it is. I write down the quality of the model is a product of the quality of the individual layers. And so the log quality becomes a sum of the log qualities of the individual layers. So I essentially, this is kind of like the free energy is a product of the qualities of the individual free energies. Or the average. These are not free energies, these are averages, right? The quality is a metric. You obtain it from the free energy. So you have to treat the multi-layer perceptron as a bunch of statistically independent layers. Otherwise, the theory is just incredibly nasty. And in section 5, like in section 7, I write this sort of the beginning. This is described in a lot of our earlier papers. And then you go all the way down to section 5. I go through all this thing. And somewhere in here in section 5, where is it? Way up here. should have used the. I should have used the. We derive everything from scratch, and at some point I try to route down the. Yeah. So the quality of the neural network is like 1 minus the generalization area of the total network. So that's like the accuracy. It's like some approximation of the accuracy or maybe the precision, and I have to assume it's a product of individual layer qualities. And then what happens is, and so I have to make this approximation. Otherwise, the theory is just intractable for me. I mean, there are other people maybe who can do like the full multi-layer case. And so way down, somewhere down here, you end up with an expression. If you go through, maybe it's up higher. Here it is. You write down the self-overlap. That self-overlap object in the matrix model will look like this very nasty thing. And we'll go through this at some point. And I have to assume that the self-overlap can be approximated by these single point functions plus inter-layer cross terms. If you've done like in more advanced statistical mechanics, you might recognize this as some form of Wick's theorem. But the problem is that these are not square matrices, they're rectangular matrices, and they're different shapes. So I don't know how to go from here. I don't know what these interlayers. So this is sort of this is the key idea. We compute this self-overlap, which we described earlier in the paper in section 4.2. And then this is going to be a product of self-overlaps for individual layers. And then there are going to be these layer-layer cross terms. Weight Watcher can actually compute the layer-layer cross terms, but I'm not entirely sure how to integrate them into this equation. So we end up just treating each individual layer as if it's a statistically independent thing. That's sort of like the long answer of what's going on. And we'll get to this eventually, but I hope that's helpful.
Real quick, this is my final one.
That's why we're here.
Is the thermodynamic boundaries. I think we are referring to them as limits, right?
Yes.
So when the parameters increase, basically, it's like a rolling average. In order to keep it consistent, to keep those constraints right, without it exploding or collapsing, in a sense, we have to have those thermodynamic limits. But it's averaged. The thermodynamic limits are averaged, right? From what I was seeing, or maybe I got it wrong.
No, right.
It looked like a rolling average. If it increased, then the thermodynamic it's going to stay consistent because we're still taking the average of what the thermodynamic is at that point.
Right. That's right. Yeah. This is like no one really explains this. Like you read these papers like from the 90s, you're like, what is going on? And you realize like what they're saying is just that I have some thermodynamic average. In this case, it's the average self-overlap. Okay. Some trace of a matrix, right? Okay. I have to divide by 1 over n. Why? Because otherwise the average will blow up, right? As the matrix gets bigger, it will blow up. So the averages, things like the average energy, the average entropy, the average volume needs to say it can't blow up, and it has to, as the system gets bigger and bigger, the average self-overlap, the average free energy, these objects need to stay bounded. And in fact, they should always, so there's always some, so somewhere here I talk about, I don't know where it is, somewhere I talk about the free energy being scaling as, like early on we talked about, where was it? Like up here, this idea that you have this average energy, this average error, which is like an energy. And this is really only at the high. This is going to be true in the this is true in the annealed case in the high temperature limit. So I need to comment on that. And then there's a size extensive form. So this object scales as 1 over n. As the system size gets bigger, the error can't blow up. And we need this. And so in normal statistical mechanics, you might say, well, this is the entropy. The entropy is size extensive and the temperature is size intensive, because if you or the volume is size extensive, because if I double the size of the system, the volume doubles, but the pressure is size intensive. The pressure doesn't change, right? If I double the size of the system, the entropy might double, but the temperature stays the same. So you have to decide what is intensive and what is extensive. In these theories, what's happening is that you have a free energy, and you want the free energy, you want to have this when you define the error, it has to like this total error has to scale as in the infinite limit, and that occurs. And forgive me if I'm kind of over explaining. When we take the saddle point approximation, where is it? We have this integral which depends on n, right? And we want to approximate this integral by its peak value. Well, in order to do that, this thing has to decay exponentially. As n gets larger, this thing has to decay, right? This e to the minus n gets smaller. Otherwise, the integral would blow up and you wouldn't be able to replace it, right? It would just go. So that's the key idea, right? Not only are the thermodynamic averages bounded and they scale as n, but this thermal average you take, the ability to take the saddle point also means that the fluctuations are going away. So you're not only are the averages constant, but the fluctuations are going away as well. And that's what we're doing here in the SPA is we're getting rid of these thermodynamic fluctuations. And that may not be the case, right? This is independent. This SETOL point approximation is not necessarily true in the thermodynamic limit. We're just going to kind of pretend it is because we want to get a nice formal result. Does that help?
Oh, absolutely.
Yeah, okay.
Thanks for that.
Okay.
Yeah, that's why we're doing this.
That's why we're doing it.
Go ahead. Sorry, when I'm getting feedback on your side, that's why I'm letting you go ahead.
Go ahead.
I'm sorry. I was putting it back on pause. I'm actually the way I'm operating. Yeah, I'm sorry.
All good. All good.
That's it for me.
Discord should be smart. We need AI that can remove, so I don't need to hear myself twice. Once is enough. Okay, any other questions? Well, okay, great. Well, thanks for doing this, guys. I'm hoping this will help give some clarity to what I'm doing, and it's super helpful to me because you can see there's still a lot of little typos and things I have to fix. And this paper is, my goal is to just get the thing out there so people know what's going on and they can understand a little better about what the theory does. I think sometimes people think the Weight Watcher is just kind of like this weird curve fitting thing, and like, no, there's actually a theory behind it. And the goal is to develop a theory of learning where we can go ahead.
Can you hear me?
Yes.
Oh yeah. Sorry about that. Yeah, I think my microphone was off for different inputs, so you couldn't hear me. But yeah, thank you for the talk. And I mean, it's really interesting to see all this theory having such deep connections with statistical physics, statistical mechanics, and all that. I'm not that deep into the math starting, but really feel like the intuition of the renormalization group theory kind of makes sense at in a really deep level where we can kind of integrate information and matter somehow. So I mean that's also kind of the inspiration I got to develop this metric exponential approach to attention. And I mean, one of my first attempts was to actually kind of renormalize a model. So, I mean, I see how you are taking this layer-wise, but have you thought in some way to actually kind of extract this renormalization group, and given that each model is correct, then you could kind of renormalize and kind of obtain the scales and remove layers or something like that?
Well, what we know to do is we can detect the renormalization. So we know that this is this expression for the exact renormalization group, a single step of Wilson exact renormalization group, and we believe that when a model is in its ideal state, it satisfies this single step of exact renormalization group, and we can measure it. So way down in the paper in section 6, we measure it, and we show, for example, that if you look at large LLMs, we have a way of measuring it, and we'll talk about that eventually. Where is it? Way down in section 6. This really should be 10 papers, right? It's too much. Here we go. So this delta, the y-axis, is a measure of the how well the model satisfies the exact renormalization group transformation that we predicted from the theory. This is predicted. And the x-axis is how well the model performs based according to the HCSR theory, so the alpha metric. And what you can see is that now the HCSR theory predicts that when alpha equals 2, a model is ideal. And the SETOL theory predicts when this delta gamma is 0, a model is ideal. And you can see they line up, right? You can see as alpha approaches 2, the delta approaches 0. And as alpha is less than 2, the delta actually drops below 0. We see this with VGG. We see it with ResNet. We see it with visual transformers. We see it with DenseNet. We see it with Falcon with Llama. Llama 65 in particular is a really nice. So we're actually able to we see this, and we see it in training our own small models. Somewhere in here I have somewhere in this append. Here it is, and we see it on our own model. So if you and this is reproducible. If you take a multi-layer perceptron and you train it on minced and you adjust the learning rate, you can get the alpha to drop to 2, and the delta in this condition will hold. So so it suggests to me that the alpha equals 2 is in the language of statistical mechanics is a universal critical exponent, which is, so the renormalization group transform is being characterized by this universal critical exponent. I can't prove that yet. I can't prove it. I suspect it. The empirical results suspect it. And, if I were a professor, and, I didn't have to, have clients and deal with investors and things, I would try to prove that. But I think that's what we know. And so how do you use it operationally? Well, and I think that's your second question, like, what do you do with it, right? You know it. Okay, well, that's the next step, is to figure out how do we design optimizers and learning processes that can drive every model to this state. So every layer in every layer in a model would be 2. So in ResNet, for example, the ResNets look like, where's the ResNet? ResNets look really good, right? The ResNets are like one of the things, like this is the ResNet series. This is a really nice plot. Like a lot of the layers are right here, but not all of them. How do we get every layer down to alpha equals 2? And how do we get every layer to satisfy renormalization group? And should it, right? Maybe, or should it within some boundary, right? The HCSR theory is sort of like, as long as you're within this region, things are well. So that's sort of operationally like the challenge. Like,
Okay.
right? That's what we're trying to do.
Yeah, it's pretty cool. It's pretty cool. Another question that might be more speculative even, but not sure if you've thought about that. I mean, I understand the idea of renormalization as, a way to kind of like acknowledge how do you traverse across scales.
Right.
So this intuitive thought makes me think about language, which is really a hierarchical scale thing, right? So, I mean, just if you think about characters, words, phrases, concepts, and documents, sometimes I'm thinking about this renormalization group theory being really helpful for that, because if you kind of get that exact renormalization or whatever, I think that could be like a map to go from all those scales naturally. So kind of if you have a concept, then you could kind of go deeper in resolution and explain the concept.
Yes. I think So I think most people, when they think about renormalization group, they think about in 2 ways. They think about it in the Kadanoff way. So the Kadanoff way, and I have a blog post on this. The Kadanoff way is sort of saying, well, every layer, as you go down in the model, as you go from one layer to the next, each layer is a different scale of the features. So each layer represents the features on a different level of coarse graining. And that's kind of like Kadanoff variational renormalization group. And there was a paper, from almost 10 years ago that described it that way. Other people, when they think about renormalization group, they think about, okay, if the individual layers are rescaling, then you say, well, there's some sort of fractal behavior or scaling behavior in the weight matrix itself. And somehow in the language is doing within the weight. So the scaling can occur either from one layer to the next or within the weight matrix itself. And that's absolutely correct. I think that's the case, that you have these sort of different concepts and the concepts connect together. And, there is some, I'm not a specialist in mechanistic interpretability, but I think, that would be sort of where I'm trying to understand better what's happening. The way it's described in our paper, in my paper, is really, it's a much more technical thing where you have this, it's this very, very technical thing that we use to detect it. And we know that, so it's not a Kadanoff approach. Of course, it's equivalent, and eventually it'll be equivalent. But it's this very technical thing that you have this HCIZ integral, which takes this form, and you do this change of measure, which is this change of measure where you go from the weight matrix to the correlations, and this change of measure satisfies a volume preserving transformation, which is equivalent. So we sort of go through this sort of change of measure where the determinant has to be equal to 1, and you end up with this condition where if you look at the eigenvalues of the spectral density, half the eigenvalue, the log of the eigenvalues, half will be greater than 1, the other half will be less than 1. You sum them up, you get 0. You satisfy this, I'm kind of like paging through the paper, you satisfy this renormalization group transformation, which is related to this. And so the paper sort of uses this, I'm thinking somewhere in the paper I talk about, it must be earlier, right, where I talk about this is equivalent to, what we're doing is equivalent to taking one step of Wilson renormalization group. But I know I don't really like I derive all of it from scratch. Like the entire paper derives the Wilson renormalization group from it derives this condition from scratch without having to know any statistical mechanics. And it arises because of the power law structure of the spectral density and the way in which you have to evaluate these integrals. And so the question being, when you ask, well, how do I find this scale within the weight matrix itself? Well, I don't know, right? Like it's a mathematical prediction of what the spectral density should look like somewhere inside the weights and the eigenvalues and the way the singular vectors are organized. Somewhere the concepts are there, but I don't know like yet how to get them out. Right. So again, I'm sorry I give like a long answer to a simple question. I'm sorry.
Yeah, no worries, no worries. I mean, I'm thinking somehow
it's in there somewhere,
like,
right? I don't know how to dig it out, right? It's in there somewhere. What I'm saying is that we didn't start there. I started from the pure math and just empirical observations, and then realized this has to be true. So,
I mean, applying this to kind of like an icing model or things like that, where you could have like theoretical values of those scales and stuff, and then like capture them and see how they arise in the actual weights. Maybe that could be an interesting idea.
There may be people. I think there's a paper of someone trying to do this. It recently came out that, like, people are beginning to discover that there's like you can apply renormalization group. We didn't do anything like this. Is just I just don't know where like you'd have to look inside the weights and figure out how they're related to each other. I think that's what you have to do. Yeah.
I mean, also, I think a critical step would be kind of decomposing of layers, right? Like you can look at a single layer and capture all these, but then how do they compose? That's where everything...
Right. We're not making a statement about how the weight matrices are organized, and we're not saying anything about what the optimization process looks like. We're just saying that when you look at a model And if you just peek, like if you're a chemist and you're doing like a laser experiment on a molecule, or you're an experimentalist, or you have an X-ray machine and you're looking at the X-ray machine, a guy comes into the gym and you do an X-ray on him, he's got no body fat, right? You do a DEXA scan, he's got 3% body fat, all his muscles are very dense. He's in good shape, right? I don't know how he got there. I don't know how he got in good shape, but I can tell someone who's in good shape from someone who's not by doing an X-ray. How did you get in good shape? I don't know. Like, you did something that got you in good shape. Tell me what you did and I'll try to do it. It could be genetics, right? Maybe you have good genetics. There are guys who are just, some guys, they eat whatever they want. They never put on any body fat. Could be, training.
I mean,
it's the same thing here. Like, we know what the ideal models look like, but we don't know why yet. We don't know how they got
like there. You can see a single layer and apply this, but then comparing all layers hasn't shown any difference. I mean, in a good model where all layers are well behaved, like, there should be something that pops up after.
Well, I mean, the one thing we know is that the models that look the best are the models that look the best are the ResNet models. Like, if you look at ResNet, it looks great. Like, there's something about those residual connections allow information to flow between layers in a way that all the layers converge according to our theory. All the layers look like they've converged ideally, except for last, and we published that years ago. That's 2021 work that was done in 2018, so it's almost 10 years now. It's 7 years that we knew that the ResNet models look like this. The ResNet models are very, very highly optimized.
Okay.
With LLMs, I don't know yet. Like how do we get LLMs? My approach, how do we change the optimization training process? Can we adjust the layer learning rates? Can we adjust the way layer normalization works? Can we, change the size of can we change the dimensions of the layer weight matrices during training to optimize them to the data set? And how many epochs do you need to run to do that, right? There's this, how do you get a really good model? There is this challenge that training models is expensive. And we know that if you train models for longer, they get better, right? We know that. I mean, that's been known for long. If you train them, but you have to be careful that you don't have to need early stopping, that they don't overfit.
Yep.
But the problem with training models that are ideal is that it's very expensive. I think it's easier to train a really large model and to have a lot of layers that aren't quite converged, and then to try to distill it down than it is to try to train the model exactly, like to an ideal state. It's just more expensive. And we're trying to, obviously, to make models to people to get, so there are a number of things, and we don't fully understand also. I mean, I'm not going to claim that we understand everything, right? It's not obvious to me that every layer needs to be alpha equals 2. Maybe that's not correct. We see it with ResNets. So, and we see, and in the paper, we show that we can, by adjusting the global learning rate, we can optimize a model. What happens when you try to adjust the individual learning rates on each layer? Like, that's the next experiment. Can we fine tune a model to give optimal performance just by looking at the layer spectral densities and just by looking for this renormalization group condition? And how close do you have to be?
Or maybe computer the gradient. For example, they did something in the Gurking paper. They applied the spectral methods to boost the learning, facilitate the generalizing aspect.
Can you tell me more about that?
Yeah, but basically, I think in the third Gurking paper, what they came up with, basically empirically, they just applied the high pass filter, I think, on the gradient, which they established and parameterized by a Fourier transform, and they observed that this boosted their Gurking speed, because they only trained for modular arithmetics then, I think.
That's very interesting. That's very interesting.
Yes.
Yeah, I that's why I like to do these talks. There are every day 100 papers are published. No idea what's going on, right? It's so hard to know what's going on.
Can you send us the link of the paper?
You just have to renormalize. Shouldn't be that hard, I guess.
Well, I don't know what the renormalization procedure is. I just know that we just think that in the ideal state, you get to this, in the ideal state, we see that the renormalization condition is satisfied. So this is like, it's a condition for optimality, but we don't know. Again, it's like this idea. I know I need to lose weight. I don't know how to do it, right? I can't do it. I know if I were leaner, I'd be stronger, right? But is it genetics? Is it diet? Is it training? Is it, what is it? It's this theory of what is it that actually makes it happen? And, the one thing we think is that adjusting the learning rates can help. That's like the big thing. Probably the biggest thing we have is adjusting the layer learning rates. Because, when you train a model, every layer, there are two or three main things that are adjustable knobs. The learning rate, the amount of regularization, the amount of dropout, and the size. Right, but there's another thing like I saw a post recently on Twitter just the other day. Someone has come up with some new kind of layer normalization scheme, which tries to control the variance better between layers, and they claim that they can get rid of a lot of these. They can get the layers to converge better just by controlling the information flow, by controlling the layer normalization. And that's obviously the theory doesn't tell you anything about how the layers are normalized and how this is this problem of this cross, like there are these cross terms that appear in the theory, right? As I showed, there are these cross terms that appear. I don't know how to deal with them. I know they're there. You know that if we had a good theory that could tell us what the cross terms were and how to deal with them, you might be able to say something about, well, what should the layer normalization look like? How does the layer, I think in this case, they rescale the layer normalization by like the square root of the depth or something like that. And that somehow that gives you much better convergence. But, I have no idea why that works. I think they're just trying, they sort of have a heuristic. But that's kind of what we're trying to figure out. Like, we know that like, this is more like my approach, this is more kind of like a reinforcement learning approach, right? If I were training a model, I would use the renormalization group condition and alpha as a signal for a reinforcement learning algorithm, and then just try all sorts of different things and let the reinforcement learning algorithm figure out what the right thing is to do. Adjust the layer learning rates, adjust the dropout, adjust the size of the models, change how the normalization works, things like this. But I haven't done it yet. It just sort of, we've only started scratching the surface on doing this. And if anybody wants to try it, I'd be happy to work with you on it. I think that would be great.
Yeah. Have you seen the Baker-Campbell-Hausdorff formula?
No, what is that?
I think it relates kind of, like, if you have like some results on these Lie algebras, like how you can treat the actual cross terms.
Oh, okay. That would be interesting.
Yeah, I'll share it to you.
That would be great. If you share it on the channel, that would be great.
Yeah, I'll share it there in the metrics.
In the paper, I suggest, I shouldn't have turned it off. Hold on. In the paper, I do suggest in the end. So in the conclusions, if anyone, I think Mahoney might be the only one I get to read the whole paper. I forced him to read it so many times. In the conclusions, I talk about the layer cross terms. Okay, so what I assume is that there's some form of this final norm generating function where the overlap is between two different weight matrices. So if I have sort of the overlap between a matrix in one layer and a matrix in another layer, I could then form the R transform for that object and then form this integrated R transform and analyze it. And so basically you look at the spectral density of the overlap between the different weight matrices. And Weight Watcher can do this. Like if you run Weight Watcher and you use the term intra, it will compute the spectral density and the singular value decompositions between these layers. It will attempt to identify all the various layers, the nearest layers, and couple them. I don't know what to do with it. Like what should it do? Should it be power law? Should it be heavy tailed? Should it be random? If it's power law, what contribution does it make to the cumulative? So what I expect is that the final result would look like analytically, if you're, what I expect is that if I could somehow treat the layer interactions, we go all the way back to what we were discussing earlier, that they would appear, these layer cross terms would appear, where is it? Here, right? There would be these inter-cross terms between the layers, and that somehow the final free energy would include these cross terms. That would be a typical type of linked cluster expansion. I just don't know and I suspect I know what they are, but I don't know the exact functional form. So that's kind of where I'm stuck, and I kind of punt. So I'll take a look at the paper. That would be very interesting because obviously this is just so maybe there's something there that would tell us what these terms look like beyond just what the trivia, just sort of the obvious thing that they would just look like the couplings between matrices. How do you deal with renormalization? How do you deal with relose? Things like that.
I mean, and probably that needs you to assume kind of, like what are the elements of what you are trying to learn on. I mean, this formula is about Lie groups, and I think it makes a lot of sense for language, and I mean probably also like for 3D spaces, like this kind of uh, like what's a word? I think it's like Gaussian splats. Like they really work, and it's just like blobby circular things. So I mean, maybe
It could,
loss
there
supposition.
in quantum
Yeah.
chemistry. There's a formulation of this called couple cluster theory, and I think the couple cluster theory is related to these matrix exponentials you talk about. So it's possible that there's some so and the couple cluster expansions satisfy the linked cluster expansion. So it's possible that maybe, and I've thought about this, like there may be some way of writing this as a matrix exponential using a couple cluster type expansion, but it's not entirely obvious to me. There's some
And no,
go ahead.
I mean, yeah, it's okay, and yeah, we're all trying to renormalize. So
Yeah. But we definitely can. One thing I do is this is an empirical way of detecting how well a layer satisfies the exact renormalization group. So that is something that I think is and that result does not depend on the high temperature approximation. So it doesn't depend on the functional form of the layer free energy. It depended, but it doesn't treat. But it does assume. And by the way, in the limit of the exact renormalization group, and this is a very qualitative statement, it's not mathematical, but in the limit, in the paper, we describe this thing called the independent fluctuation approximation, and so we talk about this idea that we explain why we make this approximation. It's just for mathematical convenience. But there is a notion that when you're at the exact renormalization group, the saddle point approximation is exact, and all the fluctuations between layers and between other components go away. That's the definition of that's the definition of the renormalization group point, is that you don't have to worry about other fluctuations. So you would assume that in the ideal case, when the system is at perfect, and when it's right at the phase boundary between learning and disorder, between basically learning and not learning, or learning and memorization, learning and confusion, at that point you would expect all the layers to be independent and all of them to satisfy, because that's sort of the definition of the exact. Now, I don't know if that's mathematically true, but that's sort of qualitatively what we expect, is that all these fluctuations go away, right? Because you're at the limit point. So that's sort of a justification. I would say that's like a and we have an empirical way of measuring how close you are to that. So the theory tells you how close are you to that, how close is each layer to the limit point. I don't know what the conditions are in the fluctuation, so I don't know how to measure the fluctuation. Like, I mean, I have an idea of how to measure it, but I don't know like what obviously it has to be a coupling term between the weight matrices, but I don't formally know how to do it. But that's sort of the idea, is that that's why I think a reinforcement learning algorithm would be the way to do this, because it doesn't force you to be there. It just says, the closer you are, the closer you are to the renormalization point, that's, if you get closer there, choose that. That's a positive signal. but you can
Okay.
measure it empirically, and that's something which I don't think anyone else is. Not that I don't think anyone else has come up with a way of empirically looking at a model and telling you how close you are to exact renormalization. I'm unaware of anyone who's done that. Maybe they have. I don't know that, but that's really the one of the key results.
Okay. Yeah.
And I encourage you
Well,
to use it, right? Like if you're doing it yourself, you can, and you're trying to determine whether things are renormalized, you can run the tool. You can run Weight Watcher, and you can get the result. I mean, it's not a theoretical thing. It's operational. You can use it. So I'd like people to use it and tell me what happens. Is it right? Is it not right? Does it work? Is it useful? Is it not useful? Right? I mean, I don't have any grant money, right? I don't get paid for producing papers. My goal is to give you guys a tool that you can use, and then come back and tell me whether it was useful. And if it was useful, great. If not, tell me what would be useful.
yeah. Well, thank you very much.
Hey, thank you guys.
Thank you, Charles.
Hey, thanks, guys. If you guys want to do this again next week, we can talk about something. You can go through more of this or more of the broader spectrum stuff, whatever you want to do. I'll figure something out. All right. Thanks again, guys.